And let me get started with a bit of history. So what you see here is actually a copy of the first ever scientific journal published back in the year 1665. And this journal published on just about anything you can imagine, from planets in outer space to whales in the ocean. So if you were a scientist back then, this would probably be the place to go looking for knowledge. But of course, if you fast forward to today, there is not one, but many, many journals. And to find information, you'll use a scientific search engine. Unfortunately, you are likely to come up with this in your results, a whirlwind of research. An especially serious problem is in the biomedical domain, where you have over 1 million biomedical papers coming out every year, and this number keeps growing every year. These papers have a potential wealth of knowledge on treatments and diseases and information that could help physicians and clinicians and also accelerate life science research, but we are drowning, so to speak, in this sea of information. So this raises a dramatic opportunity that is the focus of my research, augmenting and scaling scientific discovery with AI systems that can harness our collective scientific knowledge in the literature to help us come up with new solutions, with inspirations, and accelerating the scientific process. And I've been focusing on a few central pillars or themes of research. The first is extraction, organizing the world's scientific knowledge. How do we go from this massive amount of unstructured text to organize structured representations, meaningful order in this mess? For example, you can think of taking all the papers you read every year and getting a table of all the problems and solutions that were proposed for each specific problem. Second is retrieval. How do we find the information we need to help boost research and support decision-making? So for example, we've recently built systems that take information about patients who are incoming into hospital, and then we find the medical studies that are most relevant for each specific patient to help support clinical decision-making and help treat the patient. And finally, we have inference, predicting new directions, generating novel scientific hypotheses. And for example, we've been taking the most advanced recent language models, large language models that I'm sure a lot of you in the audience have heard of, and using information in the literature to help these models predict new hypotheses. For example, predict new treatments for diseases. And all of these capabilities come together into building discovery systems, new interfaces for us as scientists to interact with this information in the literature to help us discover what we need and to accelerate science. And today I want to focus on a specific project in which we are using AI to build a map of all the challenges and all directions across science and connecting the dots between them. And the driving motivation behind this project is augmenting creative discovery. How do we help researchers find novel ideas and novel perspectives? The way I like to think about this is with something I call scientific matchmaking. How do we match researchers who have a specific challenge to other researchers with specific directions? So what you can see here is a small snapshot of a huge network that we extracted from many millions of papers and many millions of authors. So each box here represents a group of researchers who share some common research interests. So for example, we may have over here researchers with a specific challenge, and then researchers with a specific direction, and these are seemingly isolated. And what we want to do is to have information and knowledge flow across this network. So researchers that have a specific problem can benefit from ideas and solutions from different communities across science. So in order to achieve this vision, we have begun with using AI to extract mentions of specific challenges and specific directions across many, many millions of papers in the literature. And now that we have that ability, we started with building a search engine to help you find the things you don't know. Right, so if you use your favorite scientific search engine, for example, to look for the connection between COVID-19 and children, you're going to find a lot of things we do know, a lot of known findings and known results. What we've started building is a search interface that allows you to find out what we don't know in specific areas. What are some interesting challenges and directions at the frontiers of science that can inspire us? And now that we have the ability to identify these specific challenges across many areas, we are also using it to find novel perspectives around a specific problem. So say you are stuck at your recent research problem, we want to allow you to think outside the box, to turn the problem on its head, to find new perspectives, related problems from other research communities, so you can get inspiration from solutions that are seemingly unrelated or unknown to you. And there's many, many steps ahead in this vision in our roadmap toward building this map. So say, for example, you want to study challenges and directions that relate to mental health and exercise, two potentially different research communities. We first want to accurately be able to pull all these different challenges and directions from all these papers into one database. Then we want to be able to group together related challenges and related directions so we can build this map to navigate all the different specific challenges and directions in specific communities. And on top of this map, we want to support novel applications. For example, so you can zoom in and get quick summaries in natural language of specific challenges and directions in specific areas. Or tracking trends and persistent challenges, finding these areas where researchers have been spending a lot of time and effort in tackling some challenge, but still are not able to resolve it. Maybe they can benefit from directions that we can automatically surface to them. And finally, that relates to identifying links between communities, links across interdisciplinary research areas, connecting between directions in different areas to challenges in other areas to help accelerate discovery. And that again relates to the main vision that I presented earlier. How do we use AI to tap into this wealth of collective knowledge, the hive mind of research, to augment and scale scientific discovery and accelerate the scientific process? And with that, happy to take any questions.
Great talk. Thank you, Tom. I wonder, how do you know what you don't know? In other words, do you have any system to make these combinations to make up fruitful directions for future research?
Yeah, so how do we know what we don't know? There was a famous politician in the United States who said there are known unknowns and unknown unknowns, right? So that may sound funny, but actually he was right. Now, what I showed you is how do we first extract the known unknowns? How do we look at the millions of papers that researchers write every year, including yourself, and then we can find specific statements that you made in your paper about things that were challenging, things that you're not sure about, uncertainties, limitations, gaps in knowledge, and also promising indications, things you found surprising, things that you want to look into further, all these statements can be aggregated across so many different researchers so we can get a picture or a map of what scientists say they don't know.
Thank you.
Again? It's working? Okay. Hi, this is Maria from Technion. Wonderful talk. Yes, I have a curiosity about the fake news and how this treat the non-real information that which kind of information can we trust or can we not? Can you say something about that?
Yeah, so how do we actually look at scientific literature and distinguish between the more reliable papers and the less reliable papers? And indeed, that's a big problem. We have a problem of reproducibility in so many areas of science. Even seemingly high-profile papers have been retracted or proved to be wrong, right? So even us as humans, experts in specific fields, we can read a paper but actually find out 10 years later that it was wrong. So this is essentially a problem that's orthogonal to ours, right? We're not going to solve all problems in this specific effort. However, you can think of all kinds of different metrics to mitigate this, all kinds of different knobs you can add to the system. You can look at the journal, you can look at whether it was peer-reviewed, how many citations, what's the impact factor, all kinds of signals that at least correlate partially with soundness of the research findings. Of course, you can look into the sample sizes of the studies, the statistical tests that were conducted, all kinds of angles like that that together can allow you to at least get more confidence that whatever you're finding in the literature is robust.
Okay, thank you.
Okay. Hi, Sarah from the Ben-Gurion University. Very interesting talk. I wonder how you deal with interdisciplinarity in this case. So every field has a different alphabet, different words that you use, but also different kind of plots and images that can be useful for research. So how do you, let's say, teach to the AI to deal with the different communities in this sense? And a second question instead is related with kind of biases that can arise in this kind of analysis. Maybe one specific paper will arise and be always cited for some reason, or, I mean, how can you assure that there is equity, let's say, in the different kind of research with this approach? Thank you.
Yeah, great. So first question about interdisciplinarity and the challenges that that introduces into these kind of systems. So indeed, a big challenge, right? Because different communities can use different languages. We have work in AI, natural language processing, that attempts to resolve these different ways in which different communities can actually refer to the same concept. Or in some cases, different communities will use the exact same terminology, but it means completely different things. So these are big problems in natural language processing. We are making advances in training these AI models with many examples of text that the models have read, or even showing them examples of these ambiguous terms to help the model understand and leverage the context around specific terms in specific papers to understand the differences. I'll give you one example. We have used AI to find analogies. So analogies are these partially related ideas. Simple example, think about the solar system and the atom. So researchers actually, back then, used inspiration from their picture of the solar system to get some initial kind of mental image of the atom. That's an example of an analogy connecting between different areas and between different texts. So if we're able to find these partial connections, we can help detect relations across disciplines. And to your second question about bias, yeah, so as I said in the previous question, there are all kinds of different ways with which you can measure impact. Actually, in a lot of the work that I was referring to now, we try to ignore citations partly due to what you were saying. So we use the actual text, the actual ideas that are being communicated, decoupling it from all kinds of societal factors that can lead to more citations and the rich get richer effect. So we kind of break it down into two different questions.
So, Carlos Bravo from Hebrew University of Jerusalem. I was using ChatGPT the other day. I was trying to program a little bit, and I needed some code that I basically didn't know, so I was asking ChatGPT about it. And ChatGPT would return really fancy-looking answers that nevertheless made no sense. So I had to go through a very long trial and error phase that required still me to be relatively knowledgeable of what I was doing to get a correct answer. So I'm telling you this story because my question is, how close are we to this stage where someone that is a non-expert can use an AI in this kind of application reliably?
Yeah, so depends on what you mean by this kind of application, because there's all kinds of different levels to this, right? In some cases, it does spectacularly well, these recent advances in NLP. In some cases, it will fail miserably and look to us as silly mistakes, right? So there are many different problems, many different approaches. The model sometimes seems to be accurate, but actually it's generating fake content that's just written in very convincing language. So we cannot prophesize, especially not with this kind of breathtaking speed that AI is evolving these days. Currently, at least, you definitely need a lot of human involvement and expertise, especially with these very difficult domain-specific questions.
If I may ask a follow-up question, I was actually referring, I'm sorry because I didn't phrase my question very well, to this particular application that you presented today about knowing what we don't know in research
It's the
papers.
same answer.
Yeah, it's the same. Okay.
Raphael from Barilan. I was wondering, you talked before about medical prescription, and I was wondering they are already doing some trial to compare the output of a medical team and what could provide AI tool. And eventually, who will be responsible for if there is any mistake in the prescription? It will be still the team, medical doctor?
Yeah. So first of all, at least currently, again, I'm not going to prophesize about the next decade. No one should use these systems for life and death decisions without human involvement, right? So humans have the disadvantage and the limitation of taking in millions of papers and finding the specific information you need for patients. But they have a lot of common sense and experience and causal reasoning that at least currently these models are limited in, although they are actually catching up. So the combination, the synergy of human and machine also applies to the medical domain. We need the experts to be able to use the machines to complement them, not replace them. And about the second question, which was responsibility. So there may be some law and philosophy experts in the audience, sociologists. I definitely don't know the answer to that. I know that a lot of people discussing this kind of very fundamental societal and public policy related questions about what AI is going to do to society. I will leave it to them.
I have a last point, a question. We see now Europe start to probably will generate a lot of laws and regulation about AI, and do you fear it? You, as a scientist, a researcher of AI, what could be the limitation for you?
Can you repeat that?
Yeah, sure. I saw recently on the news that Europe, probably other countries, will start to think about new regulation, new laws to frame AI development and use. And I was wondering, you as a researcher of AI, will it limit your work, you think? Do you think it will be a problem for you to develop?
So if I understand correctly, you're asking about regulating AI and coming up with all kinds of guardrails around AI to prevent it from creating societal dangers and harm.
Yeah.
So definitely I'm for that. I think it's, as with any technology. It can have dual uses. It can be very negative. So I'm always in favor of thinking of how to curtail those impacts while leaving enough freedom for research. But when it starts actually going into applications with real implications on people and not just pure research, then like anything to do with people, I believe it's important to regulate, at least to a certain extent.
Hi. Thank you. It's very interesting and very relevant for my research too. So, in your case, work. Yeah. In your case, you have a lot of data, which is a problem for humans, but a great advantage for the AI. I was wondering if you ever face a problem of small data, like too small data, like for studying new fields, or I don't know, fields that are not so studied. How do you overcome problems of small amount of data, if you do?
Yeah, sure. So that's a slightly technical question, but I'll try and answer it in a manner that can appeal to everyone in this diverse audience. There's two ways to do that. First is what people are now seeing with these large language models that are trained at so-called at reading millions of papers, that you don't need a lot of supervision, a lot of kind of humans going over specific texts and saying, okay, this is the specific type of information we're looking for. The models are able to generalize across a lot of different texts, a lot of different problems and areas and domains. So this approach, which is called self-supervision, where the models teach themselves, so to speak, is currently proving itself as very powerful. And that's the main way currently to generalize to areas where we have very few examples or scarce amount of data. There's also other ways, and yes, I've definitely encountered this when we're trying to generalize to specific areas of science. So a human in the loop can also help here a lot, right? If you tell the human, okay, look at these specific examples and give me information about those, that can complement the model. So that goes back to one of my central themes, how to synergize the human and the machine, right? They have different capabilities.
Thank you.
Tom, great speak. Thank you.
Thank you.